In this tutorial, I will explain some of the key concepts in dynamic games of complete information. I'll start by explaining the difference between a strategy and an action with an example. The distinction between the two will be important in understanding the difference between Nash equilibria we covered so far and the new equilibrium concept called subgame perfect equilibria, which we often use to characterize the equilibrium in an extensive form game. We then learn how to derive a subgame perfect equilibrium by backward induction. Finally, we learn a tool called one-shot deviation principle that allows us to easily check if a given strategy profile is a subgame perfect equilibrium. Let's consider the following situation to understand why we introduce subgame perfect equilibrium and how it differs from Nash equilibrium we have considered so far. In this game, player 1 is a banker and player 2 is a bank robbery. Player 2 threatens player 1 by saying, "I will blow up the bank if you do not give me money." More specifically, the player 1 here chooses whether to accept player 2's demand or not, and then player 2 chooses whether to blow up the bank or not. If player 2 blows up the bank, then both players will die. The payoff matrix of this game can be written in the form of normal form as shown on the slide. If player 1 rejects the demand and player 2 blows up the bank, then both players die and their payoffs are -100. If player 1 rejects the demand and player 2 does not blow up the bank, then both players survive and receive payoff of 0. If player 1 accepts the demand and player 2 receives the money, then player 2 is happy receiving the payoff of 10, while player 1 is not so happy and his payoff is -5. Now, one thing to note here is that the payoff of player 1 and 2, when player 1 accepts the demand and player 2 blows up the bank, is not -100. This is because player 2's strategy is to blow up the bank if player 1 rejects the demand. And so player 2 does not actually blow up the bank when player 1 accepts player 2's demand. Now, it is straightforward to derive two pure strategy Nash equilibria of this game. In one of the Nash equilibria, the player 1 rejects the demand and player 2 does not blow up the bank. In the other Nash equilibrium, player 1 accepts the demand and player 2 blows up the bank. The latter equilibrium sounds unintuitive. The player 1 knows that player 2 will not blow up the bank if he rejects the demand. In other words, player 1 knows that player 2's threat is not credible. We introduce subgame perfection to remove such an unintuitive Nash equilibrium. Now, a dynamic game is described in an extensive form, and here is a definition of extensive form game. It is probably not so clear what they mean at this point, and so I will explain through examples. You can come back to the definition after you go through a couple of examples. The important part of dynamic game is the definition of the strategy. In normal form games, actions and strategies mean the same thing, but they mean different things in extensive form games. A pure strategy in an extensive form game is a function that takes information set H as an input and outputs an action. You will see what I mean by that in the following examples. To see the difference between action and strategy, let's take a look at an example. There are two players, 1 and 2. The set of actions in this game consists of capital L and capital R for player 1. The set of actions for player 2 consists of lowercase l and lowercase r. The set of information set for player 1 consists of H1, and the set of information set for player 2 consists of H2L and H2R. Note here that each decision node corresponds to an information set. And so H2L is an information set, and H2R is also an information set. Player I's strategy in an extensive form game is a function from information set to action of player I, where capital HI denotes the set of player I's information sets. In other words, a strategy is a complete contingent plan of actions that describes which action player I will choose at every information set of player I. For example, player 1 in the previous example had only one information set denoted by H1. And so the pure strategy of player 1 in this extensive form game is written as S1 of H1, which can be either action capital L or capital R. And so for player 1, the strategies are identical to actions in this case. Now let's consider the case of player 2 in this example. Player 2 has 4 pure strategies since there are 2 information sets and 2 actions. In this example, player 2's strategy describes a complete plan of what player 2 does given what player 1 does. Strategy 1 says, choose L regardless of information set reached. Strategy 2 says, choose L if information set H2L is reached, and choose R if information set H2R is reached, and so on. The example given in an extensive form game can be represented in normal form game. You should be able to go back and forth between extensive form game and normal form game without any trouble. Note that player 2's strategy is a pair of actions that describes contingent plan of actions. The game here has 2 pure strategy Nash equilibria. In one of the Nash equilibria, the player 1 takes strategy L and player 2 takes strategy RR. In the other Nash equilibrium, player 1 takes strategy R and player 2 takes strategy RL. Now, to see that the former Nash equilibrium is not credible, we again write in an extensive form game.